environment, which is one of the, of course, greenhouse gases. So there are tightened regulations to control that. Governments enforce strict restrictions in many countries on waste disposal systems to mitigate environmental impacts. So it becomes in every municipality a very important aspect how they could manage waste. Manage is, again, reduce the size and recycle and regain. All three. Effective technologies such as fluidized bed systems are essential for sustainable and environmentally friendly waste management. Okay, so it's not just to get rid of it, it will have to be done in an environmentally sound manner. And the fluidized bed technology offers a very good options in fulfilling that requirement. Okay, we see this growing in many countries. I have designed a couple of them for different applications in the waste management area, but especially in Asian countries and Thailand and many others, they are widely used. It plays a key role in solid waste management, and again, as I said, through incineration, it is possible to reduce the amount of waste material. And we covered this. When we burn things, we spew things out into the atmosphere. There could be a lot of hazardous components, as well as, of course, large amounts of CO2. So this has to be taken into consideration as well. There are other options available, but in the interest of time, whatever, we're just going to focus on the thermal aspects through which in using fluidized bed technology. We touched on this many times, that the processes that we can embark on fluidized fluidized beds is through combustion, gasification, and and of course drying we covered last night, and opposite of it, of course, could be cooling if it's needed. So what are the advantages of using a fluidized bed? Fuel flexibility is very important. This slide, it's not just specific to waste, but it covers a number of things that we already touched on. Solid waste is one of them. Environmental compliance, again, we talked about some very strong and practical aspects of fluidized beds in terms of emission controls, mostly in the form of sulfur oxides or nitrogen oxides, given again its operating conditions and also its ability for sulfur removal. And then something else comes out when you burn something. Combustion is an exothermic reaction. It releases heat, and therefore there's an energy conversion process that takes place. Once you're able to bring the once you're able to bring it to the ignition temperature and hope that the reaction will be self-sustaining, and then it will continue burning and release heat throughout. So what are the applications? Again, we talked about this, but as I said, you can integrate this into a power plant design if possible. If it's really, really large and you build an infrastructure that counts on sustainable amount of waste as fuel, you may consider power generation, but mostly it is in the way form of heat that is released. I'm sorry, I didn't get it. Somebody say something? Okay, yeah. Okay, I don't know if you heard me what I said last, but I'll repeat it. If if you have a large enough facility that counts on a sustainable flow of waste material as fuel, and then you can build it as a power plant. But most of the time, it is. I'm really. Um, just sorry. Just give me a second, please. Okay. I'm sorry. Can you still hear me? Okay. Sorry. But it was a. Never mind. Okay. Let's go through this. So I don't know where I went. Yeah. We can use the circulating fluidized beds successfully in incinerating waste, and at the same time do it, of course, in an environmentally sound manner, but also capture a lot of the heat from it. And as I said, if it's large amounts, then we can produce steam, turn steam turbines and produce electricity, and also we can use it as for district heating if heat is necessary. So this is an externally circulating fluidized bed. Here is the bed. Here you have wastewater treatment plant, a sludge from wastewater treatment plant coming. It's industrial waste is being fed, but you have to use auxiliary fuel to bring this bed temperature to the initial ignition temperature of the waste material sludge. So gradually you co-fire until the combustion is steady, then you shut off the auxiliary fuel if it sustains itself. Otherwise, you'll have to continue it in small amounts. So as bed material, you put sand in. As a sulfur dioxide scrubber, you put limestone in, and it produces a lot of heat. You take this heat, and in the boiler section, you boil steam. Of course, these are two closed system. Water loop is completely separate. You take the water out, but then you have ash particles you have to collect, and you have the gas to deal with. Now you need to separate. for the gas to be sent to the bag filters, you will need to cool it. Otherwise, you'll destroy the bag filters. Then you go through some scrubbers and catalytic reactor for nitrous oxides, and if there are any. In this case, there are, because you temperature and from all the waste material, you have to ensure that it's clean before it is discharged through the stack. Okay, so this is externally controlled. This, as I said, it is uses scrubbers and all the other things in order to okay. The Again, what could we use here? We can use the solid residues from here, collected and treated to avoid environmental harm. The Usually ash, if it's coming from a power plant, coal usually, but other cases, you wonder what you do with ash. What do you do with the ash? Just think about it for a second. So you can use ash. It's one of the main filler material for example, road construction. Okay, it can be used as a construction material, not as a sole, but as filler or auxiliary material. So there are lots of use of it in construction industry. Liquid residues, okay, they have to be discharged properly, or they have to go through a second incineration process. Integrating the process with, again, capture the heat, and environmentally, now you have reduced the size of the waste significantly. You released as clean gas as possible, and within acceptable limits and standards. And at the same time, you produced useful heat, either for power generation or district heating or process heating. Internally circulating fluidized bed, as the name implies, instead of doing it externally, you circulate this within the bed. This is a unique design. You will recall from your fluid mechanics, there is sudden contraction, and then sudden expansion. When the dense bed is here, gases are released with some particles, they enter into a large area, and then there, around wall, there's recirculation patterns, and then they are thrown out, and then they come back. So it is a very effective internal circulation system. It is, again, if you do not, this is for smaller loads, but it is extremely effective and a simpler design than the circulating one, of course. Basically, operating temperature, as we all said, this will be around 900 degrees. And around that temperature, you minimize NOx formation. Then, as you see here, you don't have very expensive scrubbers and catalytic converters. So, what are the other kinds of incinerators or waste to energy technologies? Rotary kilns and grate furnaces, they are two most popular ones, and they usually, the operating ranges are different. I will show you, but given the rotary kiln. Let me go here, show you first what it's like. This is the kiln. It is usually its length to diameter ratio is about at least 8 times length to diameter. As you can see, it is placed inclined to facilitate better movement, and of course it rotates. Okay, slow rotation. With all these, enable use primary and secondary combustion chambers within it. You can reach high temperature. Therefore, it is very, very useful for the treatment of hazardous waste. Okay. Two very important parameters in destroying hazardous waste. Think about it, what it will be. Temperature. It has to be at high temperature. And at high temperature, how long you keep it there. So residence time and high temperature. There are two essential things that will make sure that these hazardous waste is destroyed. You can adjust the within, of course, given operating conditions, residence time, given the by adjusting the rotational speed. Again, as I said, toxic material substances, especially that could be considered very hazardous, like petroleum coke, anything with polyaromatic hydrocarbons in it, and those are they have to be destroyed before anything is released. Again, it can be in diverse, it can handle diverse range of materials. Doesn't mean that you have to just burn or incinerate toxic substances. You can do it together with some other materials. But anyway, this is what it is. The great furnaces, very simple, great moving back and forth, collecting the ashes underneath. It is it's a simple design. It is used for non-hazardous municipal waste and primarily used to reduce waste volume, decreasing the quantity to approximately 1/3. Then we have the fluidized bed combustors. Again, it's a more modern technology than those two, mostly predominantly for non-hazardous waste, but includes sludge and other pre-treated materials. Okay, very effective for energy recovery, and you can use it again to scrub the gases effectively. So this is the rotary kiln, as I showed you, and this is the reciprocating grate incinerator. As you see, this is where the material is fed. Here is the combustion zone, given the inclined design, and this is reciprocating again. The movement it enables by gravity the ash to be collected at the bottom, and then air is moved. You put secondary air to burn any unburned fuel there, ensure good combustion, and at the end, if needed, you can also provide a tertiary air. This is a very simple but very, very effective design. Again, mid-sized municipalities, they prefer this one because of its ease of its construction and operation. So if you need to make a choice which one to use and justify fluidized bed, selection of fluidized bed, you can see that its full capacity is much higher than the others, and the others use much higher excess oxygen or air. But you have to make sure that the fuel, in this case waste, is properly processed. That means you have to sift all the non-combustible material out, and and um, and it has to be, again, sized in a way that, remember what I said yesterday, group D is the largest size we can go in. Group D will be around 10 millimeters. You have to ensure that you don't have larger size particles. For example, if somebody throws pair of shoes in garbage, and then you can just throw those shoes in the fluidized bed, it goes through a chopper and sized appropriately before it can be gotten rid of. Again, these are some of the things that you need to take into consideration. What kind of food you can, fuel you can feed into it. I'm sorry, I'm just passing a little fast, but I think I'm making sense. So here's an example. This is an existing facility in Austria, Vienna. It's composed of 4 fluidized beds and 2 rotary kilns. Okay, so it covers a wide range. Rotary kilns make sure that all the hazardous waste go through that, and the fluidized beds, they look after the others. Look at the numbers. 180,000 tons of municipal sewage sludge annually, 90,000 of non-hazardous waste, and 90,000, tons of hazardous waste annually. These are significant amounts. For energy recovery, it generates 56,000 megawatt hour of electricity and 440,000 megawatt hours of district heating. So it is a combined CHP, combined heat and power plant. Its fuel is waste material, and it produces electricity and feeds it into the grid, and also a lot of heat for district heating. Okay, both for comfort heating and also hot water. 1,800 tons of metals recovered through reduction and extraction. Residue management produces 62,000 tons of solid residues. Out of all of these, a lot of solid residue, which are treated and disposed of in compliance with environmental regulations. And as I said, to do all of these, they have 4. These are internally circulated fluidized beds and 2 rotary kilns, okay, to accomplish this. You're familiar with this, but it is, again, to remind you that when you, instead of burning, you have an option of gasifying the waste material. The same principles that we discussed for coal or biomass, that you provide enough oxygen to burn some of the fuel, but substoichiometric amounts to either starve to oxygen through pyrolysis, and also under stoichiometric amount for gasification. And out of gasification, you produce syngas, and then you do all kinds of things with that produced syngas. So remember, I talked about incineration, but also gasification is also a possibility. And in some cases, there is more leaning towards this one simply because of carbon dioxide capture or reduction. I'm repeating what I covered in the gasification lecture, but these are the materials that you can use as waste material. You're familiar with this, but I thought I will show it to you again, the types of gasifiers, including fluidized beds. And you're familiar with this one as well. I showed you the operating ranges of fluidized bed gasifiers. For combined heat and power from waste, basically, the dual system is used. You have the combustor incinerator. You basically accomplish this is externally, and you utilize the flue gas. You deal with it, but what you do, you circulate hot solids. Hot solids are the heat source for the gasifier. To handle waste material in the form of biomass, and you just keep going. Or you can do this indirectly, directly or indirectly. You can do this. For methanol production from waste, you can here you do the fluidized bed system here, gasifier, and then the idea is the methanol synthesis takes place here, then the purification, and you use it as fuel in internal combustion engines or in turbines. This is another way of, again, methanol production. I'm just giving these as some examples that in modern day that you can use. Methanol is an incredibly important, of course, production because it's an energy carrier. You, instead of like tons of waste or biomass coal, you put it in the form of methanol, which is a lot. It contains a lot of energy, but also transportation is a lot easier. I sincerely apologize. I flew through this, but I can't continue anymore. I have to stop here. Okay. I hope this was useful. Again, this final lecture was just a form of application, and we applied it to waste management. I may have taken shorter time, but I think the idea was to impart all the necessary information for you to have a good understanding of it, beyond which I think you will need to, of course, do your own studies and research to get more in-depth understanding of all of these, and together with some very detailed calculations. They are all available. I wish if we were doing this in the form of a 3-month-long course, I think we will have covered all of those in detail, but nevertheless, I'm going to show you one resource. Oh, it is heavy. If you can see this book, it is called Steam and Generation and Use, okay? This is an incredibly useful, this is done by a boiler manufacturer called Babcock and Wilcox. See if it is available to your library. Again, if I were there, I would have brought. It's quite heavy. But this is the absolutely the most detailed, fundamental book for a lot of the topics we covered. But it covers a much wider range of systems and very detailed fluidized bed systems. With that, I apologize. I cut it short, but I think I have accomplished my objectives that were given within the list of contents of this course. And I wish you all the best, and thank you for your attention. Okay. Yes. Yeah. Yes. Yeah. 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 Sure. Yeah, Professor Sahoo, one thing that we couldn't do is I'm still committed to have a half an hour meeting, whatever, with those faculty members who would like to do it. But give me a few days to recover, okay? And then we'll do it later. Okay. All the best. Bye-bye.
And predicting example is the predicting spontaneous reactions or the phase transitions. And going to the just previous slide, here we can see that when he is the all the disciplines are integrated, integral disciplines for designing and enhancing energy conversion technologies. For the thermodynamics, which is that is scientific disciplines governing the transformation, exchange and efficiency of the energy from one form to another, and heat transfer, that is science of quantifying, controlling how energy migrate due to temperatures. Differences is vital in the energy conversion processes. Fluid mechanics, the study of the fluid behavior. Pressure dynamics and the flow mechanics will be handled in these energy conversion technologies. And chemical reaction engineering, whether it is the gasification or the combustion, that is the chemical reaction engineering field, directing the design and scaling up the chemical reactions for energy efficient energy transformation and generations. And electrochemistry, the study of electricity, chemical reactions, interplays fundamental for energy storage and conversion technologies. Here this analysis of momentum, heat and the mass transfer will be pivotal for the predicting and optimizing energy system performance, which is the transport phenomena, but thermodynamics will play major role in these energy conversion technologies. Next. This is already discussed. Here if you see the another importance of the thermodynamics in the energy and the environment, that is system efficiency and sustainability and environmental impact. Using thermodynamics, one can define and measure the efficiency of the various systems. Example is the calculating the efficiency of heat engine. Again, for maintaining the sustainability of the environment and what is the impact on the environment. This thermodynamic offers insights into how energy conversion can impact the environment, especially regarding entropy and waste heat. This helps in designing processes which are both energy efficient and environmentally friendly. Now, if you see the thermodynamics, that is energy conversion systems, here we can see that that is work done by the pump, which is if from this the output is that is supplied is fed to the boiler where heat is supplied, and from the boiler steam is generated, that is through the turbine we can get the work output, that is then converted to the power, and the vapor can be condensed further and heat will be out. So, this is the simple just Rankine cycle. This thermodynamics energy conversion systems. So, here biogas fueled solid oxide fuel cell, micro CHP combined heat power systems, where the energy is getting that is converted, that is biogas if is supplied, that is produced from the biomass, biogas is supplied to the reformer, and then from where finally we can get the steam, and also we can get the net electric power, and their internal power consumptions whatever will be there, that can be sufficient. This net electric power will from that we can get the net internal power consumption as well as some excess also we can get from that. This is the thermodynamics also from the simplified process flow sheet. It is the for polygeneration systems, and where we are getting carbon dioxide to storage, and carbon dioxide emitted, sulfur emitted, and syngas is produced from this carbon dioxide, sulfur, water we are getting, and there also we are getting the power. Next. The fundamental laws of thermodynamics are applied, that is first law of thermodynamics, where the conservation of the energy principle is there, and first that is one of the most fundamental laws of the nature. Energy can change forms during the interaction. Total energy remains constant, it cannot be created or destroyed. So, first law of thermodynamics again expresses the conservation of the energy principle, asserts that energy is a thermodynamic property. Then conservation of law for the mass, that is mass cannot be created or destroyed, it is a closed system, no mass transfer, mass remains constant. Open systems, that is mass can enter or the leave. And there the energy forms, kinetic potential or the internal energy will be the different type of the energy, where the first law describes conversion between these forms and the energy transport as transported as heat and the work. So, fundamental laws of thermodynamics, that is second law of thermodynamics, is also applicable, that is here in the thermodynamic processes, where the process have inherent restriction. Example, heat flows from the hot to cold, not the vice versa. Second law of thermodynamics, that is introduces entropy, which can be created, not destroyed, and describes the change of energy entropy due to transport and the creation. It also processes with entropy creation which are irreversible, leading to a work loss. Implications of the second law, that is efficiency of the heat engines is restricted to values below 100%, where heat cannot be fully converted into the work, and also quality and the quantity of the energy is determined, that is energy has both quality and quantity. Processes occur in the direction of decreasing energy quality. Example, hot coffee cools down, cool coffee does not heat up by itself. Modeling and analysis of thermodynamic systems, that is some problem systems statements are there with which you can do, and step 2 will be schematic, and step 3, so whatever the assumptions for the modeling, we need some assumptions and approximations, then the governing equations, then the what are the properties, then solution procedure, reasoning, verification, and the discussions. Thermodynamic balance equations, where the systems is considered to which the energy flows and in and flows out across the boundary from the system to surrounding, surrounding to system. Similarly, work is done on the system, that is from surrounding to work input from the surrounding to system, and work output from the system to surrounding. Similarly, it occurs in the closed systems or the control mass. In the open systems or the control volume, here the mass is entered into the control volume systems, where the work transferred across the boundary, that is work from the surrounding, work is done by the surrounding on the systems, and work is also transferred from the system to the surrounding, and similarly product energy also flows across the boundary from the system to surrounding and surrounding to the system, and some mass is collected out from the system, that is the open system or the control volume. And here thermodynamic balance equations, that is closed systems, Mi mass input equal to mass F mass output, and means total mass remains constant. So, here energy balance, that is will be energy in minus energy out, that will be total energy. So, net change net energy transferred by heat and the work, change in the equal to the energy total energy or the net energy in the internals, that is kinetic energy, internal energy, and the potential energies. So, exergy balance, that is net exergy transferred by heat and work, that is x in minus x out minus x destroyed, how much energy or the heat and work gets destroyed, that is x destroyed, equal to the delta x systems, that is change in exergy. Thermodynamics balance equations, that is open systems, mass in minus mass out is the net mass in the systems, and energy balance similarly energy in minus energy out is the net energy in the systems. So, energy transfers by the heat, work and the mass, and the net energy, that is the change in internal kinetic, potential, all sorts of the energy existing in the system. Similarly, exergy balance will be x in minus x out minus x destroyed, that is the delta x systems, which is the change in the energy, and this exergy transfer gets done by the heat, work and the mass. See example one on the balance equations for this thermodynamics concept. A textile plant requires 4 kg per second of the saturated steam at 2 megapascal, which is extracted from the turbine of a cogeneration plant. Steam enters the turbine at 8 megapascal and 500 degree centigrade at a rate of 11 kg per second and leaves at 20 kilopascal. The extracted steam leaves the process heater as a saturated liquid and mixes with the feed water at constant pressure. The mixture is pumped to the boiler pressure, assuming an isoentropic efficiency 88% for the both the turbine and the pumps. Determine the rate of process heat supply and the net power output. The solution is this: for the problem state, as combined heat and power facility is designed to produce electricity and the process heat. Some steam taken from the turbine at a high pressure, which is used for heating, and the facility's heat output rate, the total net power generated and the plant's efficiency need to be calculated. So, here assumptions: steady operating conditions exist. Second assumption: kinetic and the potential energy changes are negligible. This thermodynamic balance equations for these solutions, the schematic of the diagram of the system, schematic diagram for the systems is shown here. Here we can see that how the that is heat is process heat is that is transferred, that is to the boiler where heat is supplied, process heat, then it is from this steam generated, that is passed through the turbine. From there heat is it is a combined heat and power. So, steam is generated as well as the electricity is generated. Now, the steam is condensed in the condenser and that heat is it is transferred to the process heater, and then the that is in the condenser, whatever the that is steam will vapor will be condensed, that steam again we can be recycled to through this, because its heat will lot of heat will be there, and from the process heater also we can get the power that also can be fed to the boiler, means for the internal energy consumptions. Next. So, thermodynamic balance equations solutions, that is rate of process heat supply, that is Q process mass into net enthalpy, that is m dot 7 into H7 minus H3, where that is m dot 7 is the m dot 3, that is from the mass balance for the process heater. M dot shows the mass flow rate, and H7 and the H3, the difference is the enthalpy values at stream 7 and stream 3 enthalpy, that is the thermodynamic property. which use steam tables to define the enthalpy values with the two independent properties, and for different substances one can get need to employ various property methods, that is to define their thermodynamic properties. Several commercial tools are also available. By choosing the appropriate property method, one can estimate the thermodynamic properties such as enthalpy, entropy and the specific volume. Now, using turbine isoentropic efficiency, one can calculate the enthalpy at the stream 7. So, it is the efficiency that is for the turbine where H6 minus H7 divided by H6 minus H7. So, thus at the pressure 6, that is 8 megapascal, temperature 6 for the 6th stream 500 degree centigrade. So, from this H6, that is enthalpy from the steam table, it can be obtained. So, 3399.5 kilojoule per kg, and here S6, that is 6.7266 kg kilojoule per kg degree Kelvin. So, for the 7th stream pressure is 2 megapascal, and S, that is S7 S equal to S6, which is from that again enthalpy for the stream 7, that is 3000.4 kilojoule per kg. Now, for the again enthalpy, that is the H7, which is H6 minus efficiency into H6 minus H76, means side stream of the 7th stream, H7S. So, thus H7 is calculated 3048.3 kilojoule per kg. Now, next step one should find H3, that is using steam tables. So, where it is H3 equal to HF at 2 megapascal pressure, which is 908.48 kilojoule per kg, assuming no pressure drop for the process heater. Now, Q for the process heat transfer for the process m dot 7 H7 minus H3, which is calculated, that is 8559 kilowatt. Now, the power output which is W dot net, which is turbine work done, that is work output from the turbine minus the work in to the pump P. So, thus it is work out from the turbine is m dot 7 into H6 minus H7 plus m dot 8 H6 minus H8. So, work done by the pump, work input to the pump is m dot 1 into W P1 dot means at the inlet what is the work done, work input to the pump. So, plus m dot 4 work done at the P2 inlet point. So, thus it is W P1 at the inlet is V1 into P2 minus P1 by efficiency of the pump. So, and W P2 at the inlet, that is V4 into P5 minus P4 by efficiency of the pump. So, thus H1 which is the enthalpy of the feed at 20 kilopascal, that is 251.42 kilojoule per kg, and velocity which is Vf at the, or sorry, not the velocity, that is volume per unit mass, V1 equal to Vf at the rate 20 kilopascal, that is at 20 kilopascal pressure is 0.001017 meter cube per kg. So, work input at the P1 is calculated to be 2.29 kilojoule per kg. H2, which is H1 plus work done at the P1 point for input side. So, and H2 is found out to be calculated to be 253.71 kilojoule per kg. Energy balance for the mixing chamber, which is calculated to M3 dot into H3 plus M2 dot into H2, which is M4 dot into H4, that is H4 is 491.81 kilojoule per kg. Now, V for specific volume at the for the stream 4. So, which will be Vf at the rate Hf equal to 491.81 kilojoule per kg will be 0.001058 meter cube per kg. Thus, work input at P2 for the inlet side, so 7.21 kilojoule per kg. So, finding the H8 from the turbine isentropic efficiency, that is P8 is 20 kilopascal, S8s is S6, which is H8s, and that is 2215.5 kilojoule per kg, and turbine efficiency H6 minus H8 divided by H6 minus H8s, which thus H8 is 2357.6 kilojoule per kg. So, thus net work done, that is W net dot is 8603 kilowatt. Now, thermodynamic analysis with the innovative technology integration. In the problem definition, when it comes to creating fuels and the chemicals through gasification, that is coal gasification or the biomass, a major challenge is the resulting gas law, gas low hydrogen to carbon monoxide molar ratio, and this ratio often does not meet the specific requirements for Fischer-Tropsch or the DME synthesis, even though it can vary based on the type of the feed used. One way to address this imbalance is using the water gas shift reactor to upgrade the gas. However, while this can be effective, it reduces carbon efficiency across the entire plant, which increases the carbon dioxide emission and raises the capital and processing expenses. Alternative methods like steam methane reforming provide hydrogen rich syngas, but they come with their own challenges. For example, steam methane reforming is highly endothermic and can lead to carbon dioxide emissions due to the combustion of the natural gas or for heat. So, thermodynamic analysis with innovative technology integration. Here the two figures are shown with the co-current configuration and the counter current configurations. Here the innovative technology integration, here the integrated systems which uses the gasifier. From the gasifier the syngas is produced, and that is combined with the that is a tubes with the catalyst, that is a reactor. So, thus here the syngas provides the or used as the feed to this reactor, and here we can get the that is hydrogen rich syngas and cooled syngas. That is depending on the requirement, we can maintain this catalyst type and the temperature in the reactor. And in the counter current, here we are using also syngas from the gasifier, and here we can see that natural gas and the steam here also supplied to this, and here we are getting the output the top at the top hydrogen rich syngas we are getting, where in the co-current we are getting the hydrogen rich syngas at the bottom, and here the in the co-current it was the hydrogen natural gas steam was fed from the top also along with the syngas, but here in the counter current syngas and the natural gas and steam are flowing in the opposite direction. So, this proposed concept for the integrating radiant syngas cooler of an entrant bed gasifier with steam methane reformer is shown here. Thermodynamic analysis with innovative technology integration, that is here it is shown that radiant cooler and then the that is steam gas reformer, where we are getting the natural gas and the syngas combined, and catalyst also used, that is spherical catalyst, which helps in the conduction, radiation, and also through which the diffusion also takes place, and conduction takes place through the wall, and natural gas steam is supplied from the bottom. So, output will be natural gas and the syngas. So, that is a coal gasifier. Here in the second diagram, right side diagram, we can see that here the coal gasifier, that is the from that we are getting the we are supplying the oxygen and the coal slurry from the top, and which will be gasified. Then the here the at the bottom it is natural gas and the steam are supplied. So, on the side we are collecting the coal syngas, and from the top we are getting the natural gas syngas, combined natural gas and syngas, that is the hot syngas we are getting. Thermodynamic analysis with innovative technology integration, that is biomass, natural gas and the nuclear to liquid fuels and the power process structures. So, this is the combined biomass is there, natural gas is there, and also the nuclear energy also here combined. So, here finally, where the hot or the syngas and the cool pure clean syngas will be obtained. So, next. Again integrating the reduced order steady state model. So, with the models also the this all the technologies can be integrated, and from which one can have the idea how much net energy will be generated. Then finally, system efficiency can be calculated, that is energy efficiency, which will be energy of the fuel products from the systems divided by energy input to the systems. So, here the systems might produce a variety of the outputs, including the beneficial byproducts, clarify which outputs are determined deemed valuable or the useful, and then determine the what constituents the main inputs to the systems, and then identify the key or the significant forms of the energy involved. Here system efficiency. So, it is complicated, the just flow sheet is shown here. This is also a flow sheet for the system efficiency. Next. Here energy efficiency of the systems we can calculate using hydrogen mass flow rate into low heating value for the hydrogen divided by coal mass flow rate into low heating value of the coal. Exergy efficiency we can calculate, that is for the systems hydrogen flow rate, mass flow rate into exergy of the hydrogen divided by mass flow rate of the coal into exergy of the coal. So, exergy of the coal means specific energy of the coal in kilojoule per kg, exergy of the hydrogen, that is specific exergy of the hydrogen in kilojoule per kg, lower heating value, that is in kilojoule per kg, mass flow rate or the flow rate of the coal in to the gasifier which is feed for the gasifier in kilojoule per kg per hour, and MH2 dot, that is hydrogen production rate in kg per hour. Okay, that's all. It is the material was given by the just by the foreign expert as he was ill, so he could not deliver. So I just displayed all the that is PPTs, and as it is his material, I just overall just read it, and wherever possible I just told something. Otherwise, this simulation part and the complicated flow sheets, as I am not aware of this, I could not explain this. Thank you.
sphericity of 0.86, and a density of 1,200 kilogram per cubic meter are to be fluidized using air at 25 degrees Celsius and 202.65 kilopascal absolute pressure. The void fraction at minimum fluidizing conditions is 0.43. The bed diameter 0.60 meters, and the bed contains 350 kilograms of solids. What you're asked to solve for are the following. Calculate the minimum height of the fluidized bed. Calculate the pressure drop at minimum fluidizing conditions. Calculate the minimum velocity size of 0.1 millimeter, sphericity of 0.86, and a density of 1,200 kilogram per cubic meter are to be fluidized using air at 25 degrees Celsius and 202.65 kilopascal absolute pressure. The void fraction at minimum fluidizing conditions is 0.43. The bed diameter 0.60 meters, and the bed contains 350 kilograms of solids. What you're asked to cubic meter are to be fluidized using air at 25 degrees Celsius and 202.65 kilopascal absolute pressure. The void fraction at minimum fluidizing conditions is 0.43. The bed diameter 0.
करिबा ना मैं थ्रू कहूँ हाँ ठीक है. So let me have some tutorials, that is 3 problems we will be solving, that is for the tutorials. Problem 1 question. It is the problem 1 question is particles having a size of 0.1 millimeter, sphericity of 0.86 and density of 1200 kg per meter cube are to be fluidized using air at 25 degree centigrade and 202.65 kilopascal absolute pressure. The void fraction at minimum fluidizing conditions is 0.43, the bed diameter is 0.6 meter and the bed conditions 350 kg per solids. So calculate the minimum height of the fluidized bed. Second bit, calculate the pressure drop at minimum fluidizing conditions. Third bit, calculate the minimum velocity for fluidization. Fourth bit, using 4 times the minimum velocity, estimate the porosity of the bed. So here particle size diameter is 0.1 into 10 to the power minus 3 meter, that is 1 millimeter. Density is 1200 kg per meter cube. Sphericity 0.86, voidage 0.43, diameter of the bed 0.6 meter, data given, and air is at 25 degree centigrade, delta P 202.65 kilopascal and density 2.372 kg per meter cube. Viscosity 1.845 into 10 to the power minus 5 pascal dot second. So we need to calculate length of the bed or the height of the bed, fluidized bed, and pressure drop, and then the velocity for the fluidization, and voidage, and the velocity when it is 4 times the fluidization velocity. Here we can see the column is given here, where the L1 by Lm is 1 minus, that is length of 1 minus voidage of the bed divided by 1 minus epsilon 1, which is epsilon 1 is 0, because here we have not started supplied the fluid yet. So here voidage for velocity for the solid will be ms by density, mass by density. So it is volume for the solid will be 350 divided by 1200 kg per meter cube, mass by density. So this is 0.2917 meter cube. Now volume of the bed, which will be cross sectional area into length. So this is, so it is volume is 0.2917, which is pi by 4 d square, that is 0.6 square into L1. So from this we can get L1, which is 1.0317 meter. Now after knowing the length, here we can calculate Lm from this expression where voidage is for the bed is given 0.43. So 1 minus epsilon m is 1 minus 0.43 and epsilon 1 is 0. So it is denominator 1. Now from this Lm we are getting, which is Lm is coming 1.81 meter. So length of the bed or the height of the bed. How to skip. So first bit, calculate minimum height of the bed is over. Now second bit, here the pressure drop divided by length of the bed is 1 minus epsilon m into density of the particle minus density of the fluid into G by Gc. So here we can calculate delta P is 1.81 into 1 minus 0.43 into 1200 minus 2.372 into G is 9.81 and Gc is 1. So thus we can get here the, because delta P we are right side we are multiplying Lm, so delta P finally we are getting 12.121 Pascal or sorry 12,121 Pascal or 12.12 kilopascal. Now the third bit, where the velocity for the minimum fluidization we can calculate using the equations which given in the Kuhn-Levenspiel book. So we can calculate substituting, it is all the data whatever we have, and here 150 into viscosity into velocity for the minimum fluidization, which we will calculate. Now the sphericity and the bed voidage are given. So substituting all the data, it is on the first term it is denominator phi s 0.86 and dp 0.1 into 10 to the power minus 3 square dp square, and here the epsilon m is 0.43. So thus first term is over, only VOM minimum fluidization velocity data is unknown, which we will calculate. The second term also VOM, that is minimum fluidization velocity is data unknown. So substituting all other data, so we can get the minimum fluidization velocity, so which is so G 9.81 and rho P 1200, rho is 2.372, that is density of the gas. So thus minimum fluidization velocity is calculated as 4.375 into 10 to the power minus 3 meter per second. Now the second bit, third bit is over. So we can go to the fourth bit. When volume is velocity is 4 times the minimum fluidization velocity, that is substituting, it is the expression for the that is minimum fluidization velocity where the equation is there from in the Kuhn-Levenspiel, and in the third bit we calculated the minimum fluidization velocity as 4.375 into 10 to the power minus 3 meter per second. So for this step we can take this velocity as 4 times of this minimum fluidization velocity, which is coming 0.0175 meter per second. Now substituting here in this expression where minimum fluidization velocity is there, we can substitute there this 4 times the minimum fluidization velocity, and here we keeping the as velocity will be more, naturally voidage will be increase. So voidage, how much it will the bed voidage, that we can calculate. As velocity is known, we can keep this bed voidage as unknown, and from this substituting the velocity, viscosity, because fluid is same, sphericity of the solid particle same, diameter of the particle same, only with the velocity voidage is changing. So substituting all the data here in this expression, we can get the voidage as follows. So now calculating, so here so this is right side remaining also same, that is G into rho p minus rho 9.81 into 1200 minus 2.372. So thus here only velocity value changed in comparison with the previous step. So now we can get the bed voidage. So bed voidage is coming as 0.60498 or 0.605 we can approximate. So this is the bed voidage when the velocity is increasing, and it is 4 times the minimum fluidization velocity, where it was 0.43 corresponding to the minimum fluidization velocity, and it is 0.605. So another problem, that is the second problem, to clean and the a sand filter, it is fluidized at minimum conditions using water at 24 degrees centigrade. The round sand particles have a density of 2550 kg per meter cube and an average size of 0.4 millimeter. The sand has the properties given in this table. So bed diameter is 0.4 meter and the desired height of the bed at minimum fluidization condition is 1.75 meter. Calculate the amount of the solid needed. Second bit, calculate the pressure drop at these conditions and the minimum fluidization velocity, and using 4 times the minimum fluidization velocity, estimate the porosity of the porosity and the height of the expanded bed. So thus here data is taken from the table, and that is round sand is there, so for which diameter is 0.4 in 10 to the power minus 3, bed void is 0.42, diameter of the bed is 0.4, length of the bed is 1.75, water is at 25 degrees centigrade, for which viscosity and densities are as follows: 0.9142 into 10 to the power minus 3 kg per meter second, density 997.31 kg per meter cube, and we need to calculate ms, mass of the solid, and which is volume into the density of the particles into the bed means 1 minus bed voidage. So thus we can get the mass of the solid, because area is pi by 4 d square cross sectional area of the bed, so it is pi by 4, 0.4 to the power 2, and here length of the bed is 1.75 and area is pi by 25, 1 minus here the 0.42 is the viscosity, density is 2550. Thus this is coming 325.25 kg of the mass solid, that is first bit is over. Second is pressure drop and the minimum fluidization velocity. So, again delta P by Lm is 1 minus epsilon m into rho P minus rho into G by Gc. So, thus here pressure drop you can calculate, substitute bed voidage and densities are known. So, length of the bed also known. So, substituting all the data we can calculate the pressure drop, which is coming as 15,460.37 Pascal or 15.5 kilopascal. Now, the minimum fluidization velocity, which can be calculated using the equations given in the Kuhn-Levenspiel book, which is as follows. So, here using the data, that is porosity, viscosity, and the sphericity as round spherical particle is taken. So, sphericity will be 1, and all other data, particle size are known, here the densities are known. So, substituting all the data we can calculate. So, from the data table, although it is nearly round, sphericity here from the data table it is given 0.86. So, we are taking 0.86 sphericity and calculating the velocity is coming right side is 9.81 into rho P 2550 minus rho 997.31. So, velocity, minimum fluidization velocity is coming as 1.658 into 10 to the power minus 3 meter per second. Now, third bit, porosity and the length of the bed is required when the velocity is 4 times the minimum fluidization velocity. So, using the same equation expression for the minimum fluidization velocity, where the velocity, minimum fluidization velocity we can substitute by 4 times the minimum fluidization velocity, and from which we can calculate the porosity data, because with increased velocity porosity increases, porosity changes when the velocity changes. So, substituting the V, which is 4 times the minimum fluidization velocity, it is coming 6.632 into 10 to the power minus 3 meter per second. Now, substituting all these data we can get the in this equation we can get the porosity. So, porosity is coming as 0.6. So, we saw that porosity is changed, it is increased. Now, the length of the bed we can calculate, which is using this expression L1 by L2 is 1 minus epsilon 2 by 1 minus epsilon 1, that is porosity will be different in the different heights. And so, thus if you take L1 as the Lm is 1.75 meter, which is given. Now, the epsilon m will be equal to epsilon 1 will be 0.42, that is at the initial conditions it is the corresponding to porosity of the 0.42, our length of the or the height of the bed was 1.75 meter. Now, porosity is changed to 0.6. So, corresponding to this the length of the bed can be calculated using this equation, which is coming as 2.5375 meter. So, length of the bed corresponding to porosity of the 0.6 is coming 2.5375 meter. Now, coming to the fourth bit, sorry, with this the third bit it is over. So, now we can solve another problem. A powder of mean size 6 micrometer and particle density 800 kg per meter cube, 1800 kg per meter cube is fluidized by air of density 1.2 kg per meter cube and viscosity 1.84 into 10 to the power minus 5 Pascal second in a circular vessel of diameter 0.5 meter. The mass of the powder charged to the bed is 240 kg and the volume flow rate of air to the bed is 140 meter cube per hour. It is known that the average and the bed voidage at incipient fluidization is 0.45 and correlations reveals that average bubble rise velocity under the conditions is 0.8 meter per second. Estimate the minimum fluidization velocity, the bed height at incipient fluidization, the bubble fraction, the bed height and the mean bed voidage. So, now we can solve this tutorial, solve this problem under this tutorial. Data given, d particle size is the 60 into 10 to the power minus 6 meter, density of the particle 1800 kg per meter cube, density of the air 1.2 kg per meter cube, viscosity of the air 1.84 into 10 to the power minus 5 Pascal second, diameter of the particle is diameter of the column 0.5 meter, mass of the solid is 240 kg. That is it is volumetric flow rate is 140 meter cube per hour. So, again voidage at the incipient fluidization is 0.45 and thus here it is velocity, bubble velocity is 0.8 meter per second and the bed voidage is given. So, volumetric flow rate is velocity into cross sectional area. So, here the average velocity which is volumetric flow rate by area. So, we can get that as 140 as volumetric flow rate is given 140 meter cube per hour and area which will be. So, if you convert this that is 140 meter cube per hour and converting hour to second, we can divide by 3600. So, it will be meter cube per second and here the calculating the V0 is coming 19806 meter per second and here. So, minimum fluidization velocity we can calculate, which is 33 dp mu by rho divided to the power minus 0.1. So, thus here we can get minimum bubbling velocity, you can say. So, here it is substituting the data 5.999 into 10 to the power minus it is 6 nearly 6 into 10 to the power minus 3 meter per second. So, velocity, bubble velocity we got. Now, we can get V0 as you found that V0 is means velocity, fluidization velocity is greater than bubbling velocity. We can say that it is the bubbling bed, means more bubbles will be forming and thus here we can calculate the minimum fluidization velocity corresponding to this porosity of the 0.45. Now, similar to the first two examples, here substituting all the data and if you, as sphericity is not given, assuming that completely spherical particles. So, we can take the sphericity as 1 and thus substituting all the data we can get the minimum fluidization velocity. This is coming 9.81, means right side is 9.81 into 1800 minus 1.2. So, thus minimum fluidization velocity is 3.81 into 10 to the power minus 3 meter per second. Now, the second bit, here we can calculate the length of the bed, and here the mass flow rate already known 140 it is given, and sorry 240 it is given. Now, L1 into, so substituting the A as cross sectional area, so here we can get from the mass flow rate corresponding to the bed voidage of the 0.42. It was if you take completely static conditions, bed voidage will be there 0. So, corresponding to that length is coming 0.67906. During the fluidization, bed porosity is there, but in the static condition that is porosity is 0. So, now that we can take as the length L1, length of the bed. So, during fluidization we can take length of the bed as the L2. So, where the porosity is 0.45. So, corresponding to 0.45 we can get the length of the bed as the 1.2347. Now, third bit, we can calculate the velocity. Third bit is the bubble height, bubble fraction. So, here we know that the volume which is 0.19806 and the fraction of the bubble into bubble velocity, given bubble velocity is given 0.8, and here 1 minus FB, that is fraction of the bubble, so which is unknown, and minimum fluidization velocity. So, substituting here the bubble volume and this fraction of the bubble in the bed is coming 0.244. Now, length of the bed corresponding to at these bubbling conditions, and Lm is the bed height. So, here Lm 1.23, which is L into 1 minus 0.244. So, thus length of the bed we can calculate corresponding to this in bubbling fluidization is 1.63 meter. Because corresponding fraction of some bubble also occupying the space in the bed. So, it is subtracting that we can get the bed height. Now, here the mean bed voidage will be calculated as here mass of the solid is length into volume of the bed into 1 minus F porosity into density of the particles. So, substituting this we can get the porosity, that is here volume length into area, volume of the bed is giving, and particle density is known. So, mass rate is also known. So, voidage is 0.583 coming, or the porosity is 0.583 it is coming. Over. Okay. So, this is a few examples towards the tutorial classes on the fluidization technology, that is the fundamentals, where we calculated the minimum fluidization velocity and the if you substitute the fluidization velocity 4 times or the sometimes n times the minimum fluidization velocity, how the porosity changes, how the bed height changes, those things we calculated. And also the whether the bubbling what is the bubbling velocity, and if the type of the fluidization changing from the incipient fluidization to that is bubbling fluidization, how the porosity also changing, height changing, those things we just had the so we solved and we calculated. So, I hope this might have given some information or some knowledge how to design the fluidized bed that is equipment for the reaction, gasification, combustion, or any purpose, because these are the fundamental things we should know, that is minimum fluidization velocity to maintain the fluidization, and the bed porosity, and also the bed height. Accordingly, height and diameter of the fluidization unit can be decided, and accordingly it can be fabricated. Thank you. Any doubt? Okay. If no doubt, so we stop here. Next lecture will be for the liquid waste management. So, Professor Jena will be taking. Okay. Thank you.
ସେଟା ମ୍ୟାନେଜ୍ କିଏ କରିବ ପୁଣି ସେଠି? Hello? Hello? मैसेज लिख दो, स्टार्ट कर दो। Good morning, dear participants. My class is on fluidized bed reactor in wastewater treatment. It is three-phase fluidized bed reactor actually, where gas, liquid and solid three phases are present. As we know, fluidization is nothing but it involves passing a fluid through a static bed of solid particles with a superficial velocity enough to suspend the particles and cause them to behave like a fluid. When the fluid is introduced into the static bed of particles contained in a vessel at a low velocity, the fluid just passes through the voids of the solid particles and the bed remains fixed, which is called as a fixed bed state. As the fluid velocity is increased, the bed expands until the particles become suspended when the drag force that the fluid exerts on the solid particles just counterbalance the net gravitational force on the particles. Net gravitational force means it is the weight of the particles minus the buoyancy force on the particles as the particles are immersed in the fluid. At minimum fluidization velocity, the pressure drop across the bed equals to the weight of particles and the bed becomes completely suspended. This is the general definition of the fluidized bed and the minimum fluidization velocity beyond which the fluidization takes place. In a three-phase system, there are two different fluids. One is the gaseous fluid and another is the liquid fluid. The flow of these fluids may be co-current in the upward direction, both provide the drag on to the particles to get suspended, or it may be in countercurrent flow where the primary phase cause the fluidization by providing drag to the solid particles. So, due to the suspension of solid particles in fluidized well, the particles are of smaller size, relatively smaller size, maybe in three-phase fluidized bed 1 millimeter to 6 millimeter particle size. So smaller particle size, high surface area for the same bed mass of solid particles compared to a packed bed is there. That means it gives a high surface area, and because of the flow of the fluid, gas and liquid, intimate contact between these three phases, gas, liquid and solid, is possible, and because of high surface area of the solids, so any solid catalyzed reaction or solid may be reacting. So a vigorous reaction takes place as far as the gas, liquid, solid fluidization is concerned. That means high efficiency of the mass transfer and reaction can be achieved in the fluidized bed reactor. As the topic of this three-phase fluidized bed, that is gas, liquid, solid fluidized bed application in wastewater treatment, let us have something about this water. As we know that 70% of the earth is occupied by water, and in that only 1 to 2% of the water, usable water, that is the fresh water, rest of the water contained in the sea. And among these fresh waters also, okay, the accessible waters are not all, only a few percentage of that is accessible for our use. And nowadays, because of all this human-made things and industrialization, like the urbanization and industrialization, lot of wastes or discarded materials are find their way to these surface water bodies and contaminate the surface water bodies. So harmful chemicals find their way to these these water bodies and pollute them, which are not which cannot be used for the human being or other living animals, and harmful to them. So water is essential for all living organisms on this earth, and water contamination is one of the primary issue of the current days. So that's why when we are discharging the water to natural water bodies, we should treat them to the permissible limit, then we can discharge that. Otherwise that contaminate the water, and the availability of water for the use get reduced. So different federal bodies of the countries, they have put certain stringent environmental guidelines and regulations on the discharge of the municipal or industrial wastewater, and to meet the stringent environmental guidelines and regulation, wastewater needs appropriate wastewater treatment frameworks. There are various types of treatment technologies available. One of the technology uses a three-phase fluidized bed system, and last 30 years the interest in using the three-phase fluidized bed is increasing gradually. If I talk about the three-phase fluidized bed bioreactor alone, Since 1980s, more than 2,500 research publications are seen on three-phase fluidized bed bioreactors only. Other types of treatments are also there using the three-phase fluidized bed. Why this is three-phase fluidized bed? Because this operation is simple in its design and construction, and this three-phase fluidized bed creates close contact between the gas, liquid and the solid in the system, having a high mass transfer rate, and contributes significant points of interest for application in physical, chemical and biochemical processes, including solid, liquid and gas phases. The importance of treatment of industrial wastewater. The wide range of wastewaters having toxic contaminants and a lack of sufficient finances for treatment causes an increase in the frequency of spreading waterborne diseases, more rapid environmental degradation taking place. The table here shows the different types of contaminants. Mainly the heavy metals are listed here: arsenic, cadmium, chromium, copper, iron, lead and manganese. Few of them are the heavy metals. Iron and manganese, these are not basically the heavy metals, but others are the heavy metals. But they have the harmful effect on the human health. So this table describes the harmful effect of these contaminants, and they are primary source from different industries. As far as arsenic is concerned, it comes from paint, metallurgical processes and textile industries. Chromium, steel alloy, cast iron alloy, stainless steel, metal plating industries, then tanning industries and mines runoff, mineral processing things it comes. The table continues with other heavy metals here: mercury, selenium, zinc, nitrate, dyes, pharmaceutical waste, phenolic compounds, and the phenolic compounds are organic compounds, mainly comes from refineries, pesticide industries and many other organic chemical industries. Mercury from coal, mining, industrial waste, etc. As we can see from the harmful effects, these compounds are highly harmful and lethal to the human and other living animals. So the treatment of or the removal of these contaminants from the wastewater is of primary concern. Now let us see the fluidized bed reactor. The fluidized bed reactor is a contacting device that uses the principle of fluidization in its operation. Initially, the applications of a fluidized bed reactor had been limited to catalytic cracking when it was developed, combustion, coating, granulation, drying and other chemical applications only. Later this fluidized bed reactor was deployed for wastewater treatment. The figure here shows the basic concept of fluidized bed reactor in wastewater treatment. The wastewater is introduced into the bed of the reactor at a particular superficial velocity. Superficial velocity is nothing but the empty column velocity of the fluid that is flowing through the vessel, as if there were no solids. So what would be the velocity of the fluid if it flows through the vessel only? That is nothing but the superficial velocity. So at a particular superficial velocity enough to suspend the supported media. So as you see in this schematic, the influent, that is the wastewater, is entering through the distributor plate. The distributor plate supports the solid particles on the bed and does not allow the solid particles to fall below. So it is a porous grid through which the influent is entering to the bed, and with a sufficient superficial velocity the particles get suspended. And in the suspended condition the treatment is there. So the contaminants are either removed or it is degraded to some innocuous end product in this bed. Then the effluent we take out, and there may be recycle of the effluent if it is not meeting the discharge standard which is necessary. Here the classification of fluidized bed bioreactor for wastewater treatment. The bioreactors are classified as two-phase bioreactors and three-phase bioreactors, then upflow or downflow bioreactors. So first classification, it is two-phase versus the three-phase bioreactor. Two-phase fluidized bed bioreactor involves liquid solid or gas solid process where fluidization is brought about by the liquid or gas. But as far as the water treatment is concerned, only that liquid is there, gas is not there. And a three-phase system involves gas liquid solid process where aeration or oxygenation is added to a typical liquid solid fluidized bed reactor. In a two-phase fluidized bed reactor, fluidization is provided by the flow of wastewater through the catalyst or biomass bed, and in a three-phase system, fluidization is provided by the co-current or counter-current flow of the liquid and the gas through the solid bed. Again, another classification based on the upward and downward flow. So upward fluidization versus downward or inverse fluidization in a fluidized bed reactor. Conventional fluidized bed reactors uses solid particles that are denser than the fluid phase, and fluidization is achieved by the upward fluid flow from the bottom of the reactor. But in inverse fluidized bed reactor, which was developed later to overcome some of the challenges introducing to the conventional fluidized bed reactor, where an uncontrolled growth of biomass that affect the bioparticles hydrodynamics, that means wash out of the bioparticles from the bed, which is a characteristic of the conventional fluidized bed, that is a disadvantage of the conventional fluidized bed reactor, can be avoided using the inverse fluidized bed bioreactor. In inverse fluidized bed bioreactor, particles, solid particles of density or lighter, the solid particles lighter than the liquid phase is used. The inverse fluidized bed bioreactor is argued to possess superior hydrodynamic characteristics than the conventional fluidized bed bioreactor. Let us see the application of fluidized bed bioreactor in wastewater treatment. The application is characterized, is classified into three categories. Either it is a physical, that is adsorption, or it is chemical purely, the other side, advanced oxidation process, and in between there is a biological process. So three types of treatment process it is classified. And adsorption means it is in the fluidized bed adsorption. Biological, the treatment unit is fluidized bed bioreactor, FPPR. And advanced oxidation process, either it is fluidized bed Fenton reaction is there or fluidized bed photocatalysis is there. So by this process, in the first that adsorption only that contaminant is removed, get adsorbed into the solid matrix. But in other types, that fluidized bed bioreactor, fluidized bed photocatalysis and fluidized bed Fenton reaction, the contaminant is degraded, or for if it is organic, to innocuous end products, that is carbon dioxide and water. And if it is inorganic, then it may be converted to a valence state which is not harmful. That is possible. So among these three types of application of fluidized bed bioreactor in wastewater treatment, let me first discuss about the fluidized bed adsorption. As we know, this adsorption is an effective and economical method for the removal of pollutants from wastewater. This is the most widely used treatment technique. Every household is having one adsorption unit. Okay, the water purifiers we are having, a carbon bed is there. So when fluidized bed reactor is used in adsorption, operational problems encountered in the fixed bed column adsorption are the clogging of the bed, then a temperature gradient, local hotspots may be there, channeling of the fluid through that means all the solid particles are not come to contact of the fluid, so that the adsorption is not effective. That is the channeling. And dead zones also there in the fixed column adsorption, which is these things are eliminated by the use of fluidized bed reactor. This table shows some of the previously published work where adsorption is used in fluidized bed for wastewater treatment. Okay, large number of publications are there, but here only a few is considered. For the phenol, copper removal, other emerging micropollutants. This next the other category is fluidized bed bioreactor. As we know, this fluidized bed bioreactor has been widely used for aerobic and anaerobic wastewater treatments. The system consists of microorganisms, coated particles. That means the particles, solid particles, on to that the biomass is coated. So the coated particles of the microorganisms in wastewater, which are sufficiently fluidized, these bioparticles are sufficiently fluidized to keep the phases thoroughly mixed. So intimate contact between the liquid fluid phase and the solid phase, that is bioparticles, are possible. We get a very high mass transfer and the reaction, that is degradation of the contaminant. The support materials of a fluidized bed bioreactor normally have extremely large specific surfaces and achieve treatment levels in a shorter time than the conventional biological treatment processes, such as suspended cell systems. So here this table again gives the information on the published work where bioreactors are used in wastewater treatment. Dyeing effluent for the removal of color and COD, metal precipitation industry for the removal of copper, lead, cadmium, zinc, aquaculture effluent, denitrification, domestic wastewater. So various applications are there, and the fluidized bed efficiently remove the contaminants, as you can see. The third is the chemical process, that is the advanced oxidation process in a fluidized bed reactor. This Fenton oxidation, one of the most effective advanced oxidation process because of its rapid formation of this hydroxyl radical in a acidic medium. The process consists of a homogeneous catalytic reaction between ferrous ion and hydrogen peroxide. So in Fenton reaction, ferrous ion and hydrogen peroxide is used to produce this hydroxyl group that can oxidize the organic pollutants. So this is basically for the organic pollutants, it is quite effective. Then photocatalytic oxidation is another advanced oxidation process where the application of a fluidized bed reactor has attracted a lot of interest to the researchers, and its use in industries are also there. In photocatalysis, a semiconductor metal oxide is used as a photocatalyst to oxidize organic pollutants to carbon dioxide and water. So here the semiconductor metal oxide generates electrons, and these electrons react with the hydrogen present in, water present in the system, produce the hydroxyl group, and that reacts with the organic compound and degrade those organic compounds to carbon dioxide and water. Here another table shows the published work in the area of photocatalyst used in the fluidized bed reactor for wastewater treatment. So dyes, hospital wastewater, COD, phenol, methyl orange, another dye, these things are removed, and it is very effective. For phenol, 100% degradation is achieved, COD removal is 98%, rhodamine blue 96%, rhodamine blue another, and it is 99% also it is achieved. So now a little detail in some of the case studies you will discuss the fluidized bed reactor in wastewater treatment. First is the adsorption. One case study is the simultaneous removal of multi-pollutants in the integrated flocculation adsorption fluidized bed. So simultaneous flocculation and adsorption is there. One adsorbent is there, and then coagulation of the particle to form the flux. Okay, that means the suspended particles are there also. So it is a novel integrated flocculation adsorption fluidized bed based on the hydraulic classification theory, and the operation, performance, characterization and mechanism of the novel process are described in this particular work. In this system, 150 milligram per liter, actually it is milligram per liter. So 150 milligram per liter kaolin clay and 100 milligram per liter of phenol were used to simulate the multipollutant in synthetic effluent. So both kaolin and this phenol are considered to be the pollutant here. So removal of kaolin and phenol is done. As you see the experimental setup, so kaolin solution tank is there, then flocculant solution, okay, it is here. So the flocculant solution is pumped into the fluidized bed by means of a pump. This is the plenum chamber, means this is the distributor section which is located at the bottom, through which with intimate mixing this enters. And you see these solid dots are nothing but activated carbon, and these are hollow dots. These are nothing but the air phase is there. So then outlet is there. So this is the way it is treated. So what is achieved here? Kaolin removal, as you see, kaolin removal efficiency is shown here. Kaolin removal efficiency percentage. So in terms of Euler's number, it is explained. In terms of Reynolds number, it is explained. The kaolin removal efficiency. So a good removal efficiency of the kaolin 80%, almost more than 80% is seen. Then this is the phenol removal, CO2, CO0. Almost you see that it is reaching the value of 100% removal is there for this phenol removal. But when it is compared with the fixed condition and the fluidized condition in the same system, at a little higher superficial velocity, the second case 8 millimeter per second, it took 310 and 230 minutes in the fluidized bed and fixed bed. Obviously fluidized bed has the advantage, especially at a higher superficial velocity. Multiple wood and removal, okay, the mechanism is mentioned here. The flocculation takes place. So these are the different colors, shows the phenol solution, adsorbent, then adsorbent with the phenol adsorbed, kaolin clay slurry, solids, fox, and the turbulent direction, that means the flow, the movement of the particles. So first stage of flocculation, second stage of flocculation, then here the adsorption is there. Next, the fluidized bed reactor in wastewater treatment, a biological process. So here I will discuss this fluidized bed bioreactor for multiple environmental engineering solutions. Then inside that I will take two case studies of my own laboratory. The fluidized bed reactors are widely used for multiple environmental engineering solutions such as wastewater treatment as well as some industrial applications. Fluidized bed reactor offers many benefits such as compact bioreactor size, traditional treatment technique of the organic pollutant are oxidation rich, oxidation pond, activated sludge system where huge space is required. But if your industry is located in such a place where the land cost is and the land availability and land cost is too high, so that's why a compact treatment system is necessary where this fluidized bed system can be used. Okay, the compact bioreactor size in the case of fluidized bed is due to the short hydraulic retention time, long biomass retention on the carrier, high conversion rates due to fully mixed conditions, and consequently high mass transfer rates, no challenging of the flow, dilution of influent concentrations due to recycle flow. But there are certain disadvantages also there with the fluidized bed reactor. It is the size limitation due to height to diameter ratio. Height requirement is much more than that of the diameter. High energy requirement due to high recycle ratio and a long startup period for biofilm formation. Only that operational constants are there. In a oxidation pond, nothing is there open, just you allow the wastewater to enter to the pond, just seed it, nothing to do automatically. That it takes months of time, but degradation is there. Like a schematic of one such fluidized bed bioreactor is shown here. Fluidized bed bioreactors are characterized by solid biomass carrier, that is suspended using high liquid and gas flow rates that allow the carrier to be fluidized and behave as a fluid. Biological treatment of organic and inorganic environmental contaminants is often challenged by their toxicity and low energy yields. Main concern in the low energy yields from the contaminant degradation to the organisms catalyzing the reactions. If low energy is there, then growth of the microorganism is not significant. So these disadvantages can be removed, or the fluidized bed reactor can overcome many of these challenges, and hence have been widely studied for many applications. Here in this schematic you can see the left side that air is there, and right side here air is not there. So this is anaerobic, and the left one is aerobic. This is aerobic reactor. So for domestic wastewater treatment, biodegradation of recalcitrant organic compounds, that means very harmful organic compounds, reduction and oxidation of organic and inorganic contaminants, bioprecipitation of various inorganic compounds, oxidation reduction reactions, and bioenergy generation. These systems are used. Bioenergy in the anaerobic reactor, that is we produce. So here the industrial applications, few industrial applications I am just mentioning. The first full scale fluidized bed reactor in the United States was installed in the Reno Sparks wastewater treatment plant in the early 1980s. And also in the same 1980s, General Motors manufacturing facilities installed 12 number of aerobic fluidized bed reactors. In 1999, an industrial wastewater with a phenolic load of 1120 kg per day was treated using fluidized bed reactor having two towers of 9 meter diameter and a 8.5 meter height in Amsterdam, the Netherlands. In the same time frame, the most important commercial developments in the field was the startup of several anaerobic two-stage fluidized bed reactor plants for the industrial wastewater, where in anaerobic we get energy also, bioenergy. The first two plants were constructed in Delft in Netherlands and Orbi in France. All the constructed fluidized bed reactor systems are highly efficient due to the high biomass concentration reaching 30 to 90 kg per cubic meter, together with the efficient gas liquid mass transfer created by high upflow of the liquid velocities reaching up to 10 meter per hour. Wide application of a fluidized bed reactor have two main reasons. The first of which is to minimize the physical limitations by providing high degree of mixing of water, solid phase, and the second is to support the microbial growth and enrichment. Therefore, fluidized bed reactor allows high substrate loading rates to enrich slow growing biomass, especially for the treatment of wastewater containing toxic chemicals treatment. This technology offers many advantages because recirculation of the waste water dilutes the concentration of the influent to a non-toxic level of bacteria and provides completely mixed or semi-mixed conditions. The outstanding advantages of fluidized bed reactor systems include high concentration of biomass, very large surface area of biomass attachment, dilution of the influent with the effluent to reduce shock effect of toxicant spikes as well as higher loading rates, efficient mass transfer for all treatment systems. The main thing in this fluidized bed bioreactor system, it is the biomass enrichment via immobilization of low yield microorganisms. Aerobic and anaerobic polychlorophenol degradation, iron oxidation, anaerobic ammonium oxidation and reductive dechlorination and chloroethans are the examples of biological processes which release little energy for the biomass growth. So the challenge is the biomass growth when the energy release is less. Immobilization of microorganisms with extremely low growth yields is important for engineering applications. Immobilization can take care of this thing. Fluidized bed reactors with long sludge retention times allow enrichment of reductively dechlorinating microorganisms able to carry on the slowest reactions. Another thing that iron is a key element in the bio leaching of valuable metals from the sulfide ores. During bio leaching, iron has a key role in the bio-oxidation process affecting the microbial growth, leaching efficiency and precipitate formation. The valuable metals from low-grade sulfide minerals in bio-leaching process are solubilized with biogenic ferric ion and sulfuric acid. The final effluents from the bio-leaching process have high concentrations of dissolved iron and sulfate. So removal of iron and sulfate are necessary. So the final effluent is mainly present as a ferrous ion and has to be oxidized by acidophilic microorganisms followed by precipitation for an effective removal of the iron from the wastewater. So here this table shows how effectively the fluidized bioreactor works over the other types of bioreactor. Iron oxidation rate, the maximum is achieved 26.4 with a very low hydraulic retention time of 0.2. Okay, you can tell that packed bed also sometimes better than this fluidized bed, but here you see that the hydraulic retention time is quite large, whereas the hydraulic retention time for the fluidized bed is less. So that is the advantage of this fluidized bed reactor. Then another is the high rate of hydrogen production for the different bioreactor types, that is anaerobic system. The fluidized bed bioreactor, this is the sludge banket upflow sludge banket reactor. As you see, up to hydrogen production rate 65.5 is achieved in fluidized bed bioreactor with the hydraulic retention time of 1, whereas for a hydraulic retention time of 1 it gives a 56.6. Again, this high rate of sulfate reduction is also there. Then these reactors find the application in other anaerobic ammonium oxidation in denitrification, high rate of autotrophic denitrification, high rate of fungal fluidized bed bioreactors also. Those things I am not discussing because two examples I have shown that merit of fluidized bioreactor. Although bacteria are commonly used in fluidized bed bioreactors, the use of fungi has also received attention in recent years. Fungal bioreactors may have advantages due to their rich degrading enzymes ability to withstand harsh conditions, loading fluctuations, low pH and nutrient tolerance. Treated pharmaceuticals and endocrine disruptor compounds also. Here this schematic shows aerobic fluidized reactor for ferrous ion oxidation followed by rapid mixing unit for chemical addition, settler of solids separation and aeration unit. Here is a settler where the sludge is removed. This is the aeration unit and this is the fluidized bed. Then fluidized bed membrane bioreactors are also in use. Fluidized beds are integrated with the ultra microfiltration membranes to create fluidized bed membrane bioreactors to improve the biomass retention and performance of the process, which rely on slow growing microorganisms. So it is, you can see this is the anaerobic fluidized bed reactor and this is the membrane unit is there. Again fluidized bed biochemical systems are also there. Biochemical systems, as we know, it is the anode cathode present. So with the anode and the cathode connected electrically and they may be separated with that of the exchange membrane by the membrane, so that selectively the flow of these things are there through that. Fluidized beds combined with various bioelectrochemical systems improve their performance. Microbial fuel cells facilitate the anodic oxidation of reduced compounds such as organics with the contaminant generation of electricity, while the microbial electrolysis cells require energy input in a form of applied voltage to generate hydrogen at the cathode. So fluidized beds have been incorporated to both anodic and cathodic components in bioelectrochemical systems. So here in these schematics, that A shows one chamber fluidized bed electrolysis cell, whereas the right side shows a two chamber anaerobic fluidized bed microbial cell. This cathode chamber is external to the bed, but anode is there inside the bed. So these are certain applications of fluidized bed bioreactors. So the importance of this already we have understood now. Now I am taking to two case studies, very specific case studies on the fluidized bed bioreactor. One is the adsorption assisted biodegradation study of a phenol in a fluidized bed bioreactor. As we know, this adsorption and biodegradation are the most important methods for removing pollutants from wastewater, especially for organic pollutants. And most commonly used adsorbent is the activated carbon because of its high surface area and developed very well developed pore structure. Activated carbon, as you know, a porous carbon material, HR, which has been subjected to reaction with gases, sometimes with the addition of chemicals such as zinc chloride, before or during or after the carbonization to increase the adsorbent properties. Activated carbon is a partially amorphous substance, little bit crystalline, microcrystalline structure it possesses. So the activated carbon you see and the graphite you see the difference, where the microcrystalline structure you can see. Then the preparation of activated carbon, how to prepare. The preparation of activated carbons occur by physical or chemical activation. Carbonization and activation are the two important stages in the activated carbon preparation. The essential reaction taking place during carbonization of precursor material, that is the raw material used for the preparation of activated carbon, is the elimination of non-carbon elements, oxygen and hydrogen, are stripped off from the carbon precursor. Sometimes oxygen and hydrogen presence is also good because the functional groups are there on the activated carbon that helps in the absorption of some specific chemicals. The residual carbon atoms group into sheets of condensed aromatic system, which are often relatively irregular and disordered, leaving free interstices that may be filled or blocked by the tar deposition. So these interstices or voids are formed in the char due to the misalignment of sheets of condensed aromatic systems. So this schematic shows the activated carbon preparation, raw material, carbonization 600 to 800 degrees Celsius, char is formed, then physical activation, that is gasification, carbon dioxide and steam is used, 800 to 1000 degrees Celsius, you get activated carbon. Chemical activation, you do the impregnation, that means you add some chemicals, then carbonization and washing is there. The chemicals normally added are zinc chloride, phosphoric acid, potassium carbonate, etc. And the carbonization temperature is less, 500 to 800 degrees Celsius, this operation is there. So activated carbon is produced. Then adsorption assisted biodegradation. Activated carbon has high adsorption capacity, can maintain its adsorption capacity for a short time. It is well known that activated carbon is also a good support media for microbial growth. Thus, biological activated carbon with the attached biomass can effectively remove organic contaminants both by adsorption and biodegradation. The biological treatment processes occurs through respiration or fermentation process, in which complex organic substances are transferred into simple compounds such as mineral salts, carbon dioxide and methane. The microorganisms such as bacteria or fungi are responsible for the biological treatment process. So this is the adsorption assisted biodegradation. And as far as the biofilm is concerned, the biofilm is described as a porous tangled mass of slime or slippery matrix. It is an aggregate of microbes in which cells adhere to each other on a surface. These adherent cells are frequently embedded within a self-produced matrix of extracellular polymeric substance, forming a voluminous and a thick layer. Biofilm EPS is generally composed of extracellular DNA, protein and polysaccharides. Water is the most significant fraction of the total mass of the biofilm. It can vary from 70 to 95%. And in the dry biofilm mass, about 70 to 90% of the polymeric substances are organic materials. This table shows some of the works on removal of adsorbates onto biological activated carbons. So the microorganisms, activated carbon, phenol, the pollutants, concentration and reference. As you see, microorganisms are Pseudomonas pictorum, then Pseudomonas putida, Micrococcus spp, Serratia MTCC. These are the different microorganisms, and the immobilized materials are activated carbon, powdered activated carbon, granular activated carbon mostly, and activated carbon fiber also used. The pollutants removed here: phenol, chlorophenol, cyanide, phenol and cyanide together, methyl isobromonyl. Okay, these are the compounds. Few references are there. Where this removal of adsorbents, that means these pollutants, by the biological activated carbons are done. Now wastewater treatment in a fluidized bioreactor. So the advantages of the fluidized bioreactor already we have discussed. The problem with that is the increase in the biofilm thickness when the microorganisms in the biofilm multiply. This limits the diffusion of oxygen to the core area. Limit the diffusion of oxygen and the organic substrate to the deeper layers of the biofilm. Starvation of microorganisms at the base of the biofilm causes detach and leads to ineffective bioreactor operation. So on the solid matrix, the biofilm layer is there, and when the layer is thin, that sufficient transport of oxygen and the nutrients are there. And when the layer, because of the population rise, it increases, the thickness increases. So to the deeper layer, oxygen is not reached or other nutrient is not reached, even if the substrate, which is nothing but the kind of food to the microorganism, that is not reached, so that those microorganisms, they die. As they die, they lost the contact from the solid surface, so washout of the biomass occurs. That is the disadvantage here. Some of the literatures on the removal of this phenol and other organic compounds in the bioreactor is shown here, and the bacteria used and the pollutants that is removed, basically the phenols and polyphenols are there, and the immobilization materials, sand particles, membrane. Like earlier it was activated carbon and carbon filters were there. Now other materials also there, calcium alginate, plastic beads, membranes, etc. are used. Then phenol biodegradation by biological granular activated carbon. So in the present study, the phosphonate cell is used as a precursor material for the preparation of activated carbon. So it is about the preparation of the activated carbon I will discuss first, then the attachment of biofilm on this activated carbon, and its use in the phenol degradation, biodegradation. So the proximate and ultimate analysis of the raw materials, as you see, the volatile matter, very high volatile matter is there, phosphonate cell, that's why it is chosen. Mainly the activated carbon is prepared from different sources. Carbon was 42% to 44% only when it was treated with the alkali, that is sodium hydroxide. What is phosphonate cell? We know that it is makhana we use. So makhana is prepared from this seed. This is the makhana. This is the edible part. Now the cell of that is nothing but the phosphonate cell. That is called phosphonate. So this is the organic waste. So from this organic agriculture waste, the activated carbon is prepared. The apparatus used is a tubular furnace. The schematic of the tubular furnace you can see here, and this is the photograph of the tubular furnace. So here this nitrogen generator is used. Nitrogen is supplied in the atmosphere. Rotameter to measure the flow rate. Gas control valve is there. Flanges are there. Ceramic tube is there. This is the ceramic tube on which the boat is kept, containing the raw material. This is the horizontal tube furnace. Temperature controller and beaker, etc. are there. These are the arrangements. Then preparation of activated carbon, these are the steps followed in preparing the activated carbon. First functional cell was ground and sieved, dried functional cell was ground and sieved, soaked with 0.5 normal sodium hydroxide solution for 12 hours, washed with water and dried at 110 degrees Celsius for 24 hours. Then that was impregnated with 3 different chemicals: zinc chloride, phosphoric acid and potassium carbonate for 24 hours, dried in oven at 100 degree Celsius for 24 hours. Then activation at temperatures ranging from 500 to 900 was studied with the nitrogen flow, that is inert atmosphere, of 150 milliliter per minute. And this was soaked with 0.5 normal hydrochloric acid, washed with water, dried in oven at 100 degree Celsius for 24 hours again. Then the activated carbon is prepared. So experimental value of the parameters for chemical activation is shown in this figure for different materials, how much it is used, how much impregnation ratio is used, these things are mentioned here. The characterization of the prepared activated carbon is done by elemental CHNS analysis, surface area and pore volume by nitrogen adsorption, and identification of surface functional groups by FTIR. Then structure by X-ray diffraction. Surface morphology was studied using field emission scanning electron microscopy and transmission electron microscopy. So the instruments used are mentioned here. Now a fluidized bed bioreactor. The schematic of the fluidized bed bioreactor to the left and the photographic view of the fluidized bed bioreactor to the right, it is there. So as you see in this schematic, one air cylinder is there, that means from air compressor, the air cylinder is there where it is stored through air regulator, air is allowed to enter. Air with bacterial filter, it is allowed to enter. Then this side there is the storage tank of the wastewater is there, from which then to maintain the pH, actually acid base is added by means of a diffuser pump here. Then this water, contaminated water, phenolic water, is pumped to the base of the fluidization column. This is the fluidized bed reactor through one distributor plate, and this is the activated carbon there in here. So on which the biofilm attachment is there, that means biologically activated carbon. So then the air out is here, and then effluent from the bioreactor is coming, recycle is done. It is a semi-batch type of system. And when the treatment is achieved to the desired level, the treated water is taken here, or intermittently, to know how much degradation is there, sampling is done at this location. The equipment characteristic is given here. So I am not discussing in detail this equipment characteristic, but it is a laboratory scale. So the diameter is 4.9 centimeter, height is of 60 centimeter, and other parameters as you see. Superficial liquid velocity used in the range of 1 into 1.33 into 10 to the power minus 4 to 2.21 into 10 to the power minus 4 meter per second. And superficial gas velocity, still less gas velocity is used because liquid is the primary phase here causing the fluidization, and air is supplied okay, to maintain the oxygen level in the reactor. The density of the particles used here 1184 kg per cubic meter. Because of the biomass loading, the particles are of this ordinary activated carbon, the density will be little more. So after the preparation of the activated carbon is analyzed again, ultimate analysis of that is done. So in the ultimate analysis you can see the carbon percentage, how much carbon. In this case zinc chloride activation up to 89.77. Again your phosphoric acid activation, your carbon is reaching 68% maximum, whereas in potassium carbonate carbon is reached to 69.85%. Up to that it is there. So volatile matters removed and pores are created on this material, that's why it is activated carbon. Nitrogen adsorption desorption isotherm, that gives the information or and the calculation of surface area and the pores. So that is shown here, the BT surface area analyzer, it is done. The summary of the BT surface area, the total pore volume, micropore volume of the prepared activated carbon with zinc chloride, and is given here as you see. So what is significant here, you see at 600 degree activation we are getting a surface area, it is a very high surface area, 2869, okay, we are getting. Yeah. Where another thing that this micropore is 2124 and the mesopore is 745. So these are the very significant results obtained for this material, prepared material. Similarly with the phosphoric acid activation, a surface area of 2636 is obtained, and another important thing that the ratio of micropore, the surface area, you see that 77% almost it is there. Similarly with the potassium carbonate, okay, the surface area obtained is comparatively less than the other activators, it is only 1236 it is obtained. But this activated carbon has some specific use because of the presence of some functional groups which are not present in case of zinc chloride activation and phosphoric acid activation. So a comparison of the porous characteristics of the activated carbons from different precursors, you see the table is given, and for the present study what we have obtained. So the maximum value, earlier it was reported 2736 and followed by 2400, it was what we have obtained with a surface area of 2869, very high surface area activated carbon prepared. Similarly with phosphoric acid and potassium carbonate also, very significant values are there. So maximum it was for phosphoric acid 2081, but now we have got 2636. Similarly for potassium carbonate from other type of precursors, okay, the maximum value obtained is 1800, but we have got a less value, that is 1236. Then the pore size distribution, as you see that how the pore volume to pore width, that distribution plot is there. So the characterization is done with the FTIR. You see the peaks are there corresponding to different types of functional groups and the bonds which are summarized here. So the wave number for CH 3100 to 2850, carbon it is 1620 to 1400 in this range. OH, CO carbon-carbon triple bond, etc. These are the things for different types of prepared activated carbons. It is listed here. That means a significant amount of functional groups present on the prepared activated carbon. So then acid and basic characteristic of this prepared activated carbon. Point of zero charge is determined and shown here in this table. So the surface morphology plots of the APSM is shown here. You see that this is the Fuchsenert cell, less porous. This is the sodium hydroxide treated Fuchsenert cell. It removes some of the impurities. Now the Fuchsenert cell activated carbon prepared from the Fuchsenert cell, highly porous, you see. It is highly porous. Similarly, activated carbon, phosphoric acid, we have got like this porous structure, highly porous structure we have got, and potassium carbonate also. Potassium carbonate, this is for phosphoric acid activation. Then adsorption assisted biodegradation of phenol. The industrial wastewater containing the significant amount of phenols, as you see, phenolic resin production up to 1600 milligram per liter we get. Then your coal conversion, it is 1700 to up to 7000 we get, and in coke oven 600 to 3900 milligram per liter the effluent contains. So activated carbon can only maintain the adsorption capacity for a short time once it is available for the adsorption sites. Become exhausted by the adsorbed adsorbents, and it is well known that activated carbon is also a good support media for microbial growth. Thus, biological activated carbon with an attached biomass can effectively remove organic pollutants both by adsorption and biodegradation. it is not degraded, and up to 1700 it is 1750 almost flat. That means the microbes are dying at this concentration of the phthalate ester. Again for another 10 Ks2 the same study is repeated. The degradation profile and the tolerance study is there. Why I am showing this? Because I will compare the that thing with this one, the fluidized bed reactor, and this is suspended cell system will be compared. So the study of the internal loop air-lift bioreactor. The studies are nothing but the hydrodynamic studies, that is gas hold-up. Gas hold-up is one of the important thing because it is a aerobic system. Then gas liquid mass transfer. Mass transfer study is also done, and biodegradation. So the schematic of the system is shown here. One is the riser, that is the draft tube, central tube. The rise is there of the fluids. Then in the downcomer, downflow of the immobilized cells are there. Okay. Then so different types of the liquid and the gas phase, liquid phase, solid phase, those are used, are mentioned in this table, and photography view of this reactor is shown here. So without plastic beads is considered to be a support material for this. Without plastic bead, this operation of this reactor, as you can see in this video. So only that suspended cells are there, not the immobilized cell. Degradation is taking place there. But here with the plastic beads, so central zone you see that the rise of the beads are there, and outer of that draft tube, these are falling in the downcomer zone. This is the working. Okay, less amount of the beads are taken intentionally because this taking this video and it won't be clear if a number of beads will be more. The hydrodynamic mass transfer and phthalate ester biodegradation study in an internal loop air-lift bioreactor. Here these microbes are attached to these polystyrene plastic beads. You see these after attachment of the microbes, that is KS1 or KS2, how the SEM image, so how they look like, and this is the degradation of the dimethyl phthalate and diethyl phthalate. You see these two. Okay, one is for KS1, another for KS2. For DMP and DEP, it is there. So how much degradation is possible? Phthalate ester degradation rate. Okay, it is very less. It is, that is in milligram per liter per hour. That means per liter per hour means per liter of volume of the reactor per hour. So it is quite less, because I had shown you, it is two video I have shown. One is the immobilized cell on the plastic beads, another is a simple one. But with immobilization, you see that the middle one is for the mixed culture, and isolated one KS1 and KS2. This is KS1 and KS2. These are the things. So high degradation is achieved in the bioreactor. So gas hold-up is one of the important parameter, but more is the gas hold-up, more will be the oxygen available in the bed, and more oxygen available means driving force will be more for the oxygen to get transfer through the liquid to the surface of the solid, that is to the surface of the microbes. So gas hold-up significantly increase with increase in the gas velocity, which is shown here, and this is related to mass transfer. With increase in gas hold-off, your mass transfer rate also will be more. So you see here, this is another thing, that liquid velocity in the riser and the liquid velocity in the downcomer also in the hydrodynamic that is studied. Okay, that is not that important as we are discussing this effectiveness of the fluidized bed here. So here you see, as the gas volume is increasing, your KLA type of mass transfer coefficient, which is significantly increased with the superficial gas velocity. So more is the mass transfer, means more degradation is possible. Then batch biodegradation of phthalate esters by mixed culture in internal loop airlift bioreactor is shown for dimethyl phthalate and diethyl phthalate. Okay, you see that up to 1500 already I have shown 160 hours. Then after that the lag phase is there, degradation, complete degradation is not there, and with subsequent experimental runs, when it is repeated for a number of times, how it is decreasing. Now batch biodegradation of phthalate ester by mixed culture. This is biomass analysis, that is the growth of the microorganisms are shown here. Then biodegradation of phthalate esters by combined system, that is suspended biomass and biofilm. Biofilm means it is on the solid matrix, but as it is a recirculated system, semi-batch system, so the biomass which is getting discharged from the biofilm also, okay, they are present in a suspended state. So that's why float was there in the video you have seen. So that means biomass is present and biofilm together it is there. You see that the degradation is achieved for 1500 milligram per liter of DMP in just 120 hours it is there. And for different experimental runs, effectiveness of this system for the repeated use is gradually reducing, but it is not so significant like the previous one. Similarly for the diethyl phthalate, again it is shown here. So up to this 1750 is Hello, hello. Check. Hello. Sorry for the interruption. So here the effectiveness of this degradation you can see. So this is the advantage of the fluidized bioreactor over the other system. I am going to share one video which I forgot to share. That was for the adsorption assisted biodegradation in fluidized bioreactor. Sorry, it is one rotated view is seen here. Rotated view is there. Okay. So this is the bioreactor operation as it is getting rotated. So your treatment you see the formation is there in the tank. I continue with the presentation. Few slides I am having only. That is fluidized reactor in wastewater treatment. That is the third kind, that is chemical treatment. That advanced oxidation process. So three-phase fluidized reactor with advanced oxidation process. Your traditional wastewater treatment methods mainly focus on moving contaminants from one medium to another, whether it is carbon adsorption, moves contaminants from liquid to solid media, gas absorbing moves contaminants from liquid to gas media, and in the last 3 decades advanced oxidation process is seen to be used with significant efficiency to remove a variety of organic pollutants in aqueous solution, and came out as the attractive options for the treating wastewater having highly toxic organic contaminants such as surfactants, pesticides, coloring matter, pharmaceuticals, endocrine disrupting chemicals. This process is the simplest, cheapest, and presently considered a potential treatment method to outperform the shortcomings of biological and chemical treatment methods to eliminate contaminants. Advanced oxidation process are the methods that generate and utilize powerful but completely non-selective hydroxyl radicals in adequate quantities, which can oxidize the significant complex chemical compounds present in the industrial effluent water. Presently, fluidized reactor merges with advanced oxidation process has been concerned by numerous researchers. Fluidized reactor with AOP can be potential in pollutant reduction over conventional methods of water treatment, as it improves degradation and decontamination further. More, compared to other treatment techniques, requires less hydraulic retention time. Here here one table shows the three-phase fluidized reactor with photocatalyst slurry type. It is for industrial wastewater treatment. Different types of chemicals, contaminants have been treated. Propanol, bisphenol A, this is methyl orange, phenol, etc. Similarly, the three-phase fluidized reactor using immobilized photocatalyst for industrial wastewater treatment is listed here. Phenol, your crystal violet, humic acid, so many other chemicals have been degraded using this, and you see almost 100% this degradation is achieved for many of these pollutants. So three-phase fluidized bed photocatalytic reactor using Fenton process. It is actually Fenton process. So mineralization of bisphenol A by using waste iron oxide catalyst. This is one study. So the schematic of that is shown here, and the removal of total organic carbon TOC, you can see this is the profile is given. So the reaction, as you know, it is the ferrous ion reacts with this hydrogen peroxide. So hydrogen peroxide with this light, it is hydroxyl ion is produced, and this ferrous ion electron is generated, and finally by these reactions hydroxyl radical is generated. So this ferrous form interact with that of this hydrogen peroxide and generate this hydroxyl ion, and the hydroxyl ions degrade the organic compounds to final to carbon dioxide and water. Then mineralization of N-methyl 1,2-pyrrolidone with 0 valent iron is another study, where the degradation of the removal of TOC, you can see very good removal of the total organic carbon is achieved here. Another one is the three-phase fluidized bed photocatalytic reactor using titanium dioxide as a photocatalyst. It is a semiconductor metal oxide. So metal catalyst impregnated on porous media for aqueous phenol decomposition is shown here. So the removal with different materials, mesoporous carbon only, ozone treatment, and other types like titanium dioxide on silica, etc. are shown here. So the final it is the end product. So this reaction mechanism, we are getting carbon dioxide and water here. So what is done? Titanium dioxide, this is semiconductor metal oxide with a light source. It may be UV light or visible light can be used depending upon the band gap, conduction band and valence band, so that electron is ejected. So here you can see this hydroxyl radical is generated, and that carries out the reaction to final to carbon dioxide. So photocatalytic degradation of phenol by silver doped titanium dioxide nanocomposite photocatalyst under visible light irradiation. One study is here. So here C2C0, you can see that the degradation. There is a comparison between the UV light source and that visible light. Visible light is working well here, and TOC removal is shown here. Titanium dioxide containing mesoporous spherical activated carbon for the removal of humic acid is used. So these are different fluidized bed reactors used in the wastewater treatment. Thank you for your patient hearing. I stop my presentation here. If you have any questions, please ask me. Actually, no system in this world is good for everything. all systems have their own merit and demerit. Pros and cons are there. For specific use, okay, different things are there. Although we are moving in before 100 years, maybe bullock cart was of importance. Now bullock cart is eliminated, but it is not completely eliminated. Still, the use of the bullock cart in a specific area is there. But we have this because of the development of IC engine, we are using other types of motor carriers. We are using, okay, which is predominantly used, but that is advantages also good, but it is not completely eliminating. Similarly, when the space is available, although we are talking about the fluidized bed reactors of different kinds, even if the ordinary that oxidation pond oxidation ditch systems which are there, these are the ponds in the open space containing the microorganisms, and organic wastewater enters to that. The organisms present in the nature, they have the capacity to degrade that. But when the discharge, this contaminant which is discharge is of a high concentration, that is lethal to the microorganisms, they die. That is not effective. And if we are generating a good amount of this wastewater, and your pond is not that effective because it takes months of time to degrade that. But if we are generating to a high amount, then we have to adopt some specific treatment method. And when the space is a constant, then this type of system fluidized bed bioreactors can be used. And among the fluidized bed bioreactors, the there are inverse fluidized bed bioreactor, conventional three-phase fluidized bed bioreactor, then semi-fluidized bed bioreactors are there. So every system they are having their own merits and demerits. In the conventional fluidized bed bioreactor, the particles, solid particles we are using, they are heavier than that of the liquid phase. Okay, so energy requirement in conventional fluidized bed is a little more than that in the inverse fluidized bed, where we use the solid matrix that is lighter than that of the liquid phase. But operational, there are certain operational limitations in the inverse fluidized bed there, but this conventional three-phase fluidized bed operational constant is not that as it is there in the inverse fluidized bed system. But inverse this inverse fluidized bed system should be operated at a high gas flow rate to obtain the same amount of the gas hold up, which is easy.
हेलो 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 हरा हेलो हेलो
किसमें रूम में आम लैब रे अच्छी जा लेके आ ड्रॉर में है हाँ सही को बोल दे क्या करेगी, सही को बोल दे क्या करेगी, सही। Good afternoon, everyone. It is with great honor to welcome you all to the valedictory function of International GIAN Course 2025 on application of fluidized bed technology for a sustainable environment. Over the few days, we have dealt with thought-provoking sessions, exchanged ideas, and gained valuable insights. To commence the valedictory function, I extend a warm welcome to the esteemed dignitaries on the dais. As a gesture of respect, we would like to present a token of gratitude to our esteemed dignitaries. As we begin the program, to share the concluding thoughts and reflection of this program, I invite Professor Sushmita Mishra, Head of the Department of Chemical Engineering, to deliver the closing remarks.
Very good afternoon to all. It's a great honor for me to be here, a part of this GIAN course under our Department of Chemical Engineering. And my appreciation to Professor Abanti Sahoo Madam and Jena sir for giving their time and providing such platform for the department. My special thanks to Professor Hamdullahpur, Professor in the Mechanical Engineering Department, University of Waterloo, Canada, for giving his time for this 5 days and sharing his knowledge in the area of fluidization technology. I also thank all my students, faculty colleagues, my staff, all present in this forum. My thanks to Dean's Rick, Professor Santanu Behera sir, and the two coordinators of this program. I am really thankful that the department could host such a wonderful 5 days GIAN course. I hope the participants, as I heard, around 64 participants across the country have joined in this program, and I hope this program was fruitful, and I am really thankful and pleased that it was held smoothly and all might have gained some or the other knowledge, and it's the sharing of knowledge and their experience of our professors was indeed a great thing for the audience, and I believe the knowledge which they have gained would be utilized in some or the other way in their professional life. Thank you.
Thank you, ma'am, for your kind words and summing up the success of this course. Next, we have Professor Abanti Sahoo, the GIAN course coordinator, to provide her reflections on this course and its impact. Ma'am, please.
Thank you, Hritanki. Respected dignitaries, Professor Sushmita Mishra, HOD Chemical Engineering, Dean Srik, Professor Santanu Kumar Behera, and coordinator, another coordinator, Professor Jena, my faculty colleagues, students, volunteers, student participants, very good afternoon to one and all present over here, and also the participants who have joined online, as MS Team portal is already opened, many have joined also. So very good afternoon to one and all. And this is the closing of the 5 days program. We before the starting the program, we faced lot of difficulties because we are making online arrangement in this hall, which is our library, because we did not get the PPA because of the working days, as in the vacation only it is made available to faculties as regular classes are going on. So for which we faced lot of difficulties. Our faculty colleagues helped us a lot, for whom only we could make it successful. How far it is successful course wise, that participant will give their feedback, but as per our level, our expectation, we could delivered, but only one difficulty is we faced, that as our expert was from the Waterloo University, Canada, Professor Feridun Hamdullahpur. He was taking his class at 10 p.m. and which was getting over by 12:30, 1 o'clock, this midnight. So he was facing difficulties, and he is the emeritus professor, and because of the cold and the age also, perhaps he was having some health issues there, so he was coughing in between. So those, in spite of the several difficulties, we could conduct it, and knowing that topic as it is the fluidized bed technology for sustainable environment, as in the beginning inauguration I had told that the application, it is the mechanism, and it is a, you can say, using this technology, we can apply for the clean environment as well as for the energy production, and that's why it is mainly the faculties working on the from the mechanical background and chemical background work on these fluidization technologies. And here we found that the 64 participants, including online, offline, have registered, but on the average 40 participants were joining the classes, and we conducted that is classes, that is 13 hours of the lecture, 7 hours of the tutorial, and 2 hours in the laboratories. We demonstrated how the fluidized bed experiments are there, fluidized bed dryer, fluidized bed reactor, then photocatalytic reactor using the fluidized bed technology, and also the spouted bed. Different hydrodynamic study in the inverse fluidized bed. So all these experiments were recorded also, and I hope we have met the expectation of the participants. We don't know, we means think that we have met, they can just, it is the just beginning of the, that is sharing of the information with the participant, and now the participants are welcome to contact us whenever they need any help on this topic. If they want to fabricate at their place, if they want to use this technology in any industry also, they can, because it is mainly fluidized bed combustor, gasifiers, and all these are used in the in the industrial level also. So I think it will be much helpful, and side by side they can give attention to maintain a sustainable environment also. So with this I conclude here. Thank you.
Thank you, ma'am, for your detailed and insightful remarks. It is our privilege to have with us Professor Shantanu Behera, Associate Dean and Dean in Charge, CIRC, NIT Rourkela. Sir, we invite you to share your views of the GIAN course and your remarks.
Most respected Professor Mishra, Professor Sahoo, my esteemed colleague Professor Jena, coordinators of the program, and my other colleagues and students, very good afternoon to all of you. It's indeed a privilege for me to be sharing dais with so many great people that I have always admired, and then, you know, and I was looking at the topic, and ma'am, I recall my roommate used to be a chemical guy. So, and since those days, I think we kind of heard about and know a little bit of things about fluidized bed techniques. And I suppose Professor Roy was a pioneer in that. And I think that has transcended, you know, into this department. And thereafter, Abanti ma'am and Jena sir has, you know, kept those flag flying. And It's a wonderful technique, and probably during the times that we were studying, it was maybe a mundane chemical process to increase efficiency and things like that. But then the times have changed, and then I think this technique is there everywhere. I mean, starting from environment protection, starting from waste, remediation, to hospital waste, to water waste, and industrial, sludge and sewage, and most importantly, of course, coal-fired techniques and combustion techniques and all that. And more so, I've realized in the last maybe 5 years or so, we used to discard coal. It's a gone days technology. But then, things have changed, and coal has got so much of prominence once again, and in particular in India, and then that's also has happened in Germany also. Because about 7-8 years ago, Germany shut down their nuclear program. And there was a policy decision taken by the government. They say that, okay, after the Daiichi Fukushima disaster, I think a lot of governments re-looked at their programs, of the energy programs, and what came out of the Europe, and when you say Europe, Germany is essentially leading the way. They had actually shut down their nuclear program, and everyone started looking back at coal technology. And then the question was that how do you improve coal technology efficiency and things like that. I'm not too qualified to say on that, but then since then, the old school industrial chemical technologies have gained importance. They've come in new formats, and the way ma'am said about the participation and the kind of hours spent by the participants, it almost appears to be a full 600 level course. And it is treated by an authority, an international authority, like Professor Feridun, Hamdullahpur. And I'm not saying that Professor Jena or Professor Sahoo are less able, but then it provides you a different perspective altogether as to how these kind of advanced 600, 700 level courses are being treated in top-notch university in the world. And if this program provides an opportunity for our students, our scholars, and also our faculty colleagues to have a peek at what's going on and how people deal with it, what's the latest advances in a short full course to be conducted in 5 days, it's more than welcome. And I think, like ma'am said, I think people would have taken a lot of things from home. And generally what happens is most complex subjects, the more we are engaged, at one point we get that, okay, I understand this. It's not very linear. The understanding on complex subjects is not very linear. But the moment you are engaged with it, and then at one point just everything starts making sense. And those are generally triggered by people who are authorities in their field when they keep speaking, and from their experiences, from the way they teach things, it just happens to people attending those courses. In that sense, I thank all the coordinators, all the participants, and the departmental colleagues, and the head of the department to have patronized these kind of courses where our faculty, our students get opportunity to listen to, learn from world authorities, and it's more than welcome. I think we should have more and more of such programs. And I recall that, ma'am, it was supposed to have been to have happened in December, right?
Yes, sir.
And it sort of rolled on and all that. And on a lighter note, it's current geopolitical things are not really a good time to have a professor from Waterloo or Canada to come over to India. But that's on a lighter note. But it's good that he from there he could address our people and had a good time. So with this, I thank the organizers, and I encourage the department and all of the faculties to have programs like this. And I wish you all the best. Thanks so much.
Thank you so much, sir, for your encouraging and inspiring words. As a token of our appreciation, we will now present a memento to Professor Shantanu Behera. I request Professor Sushmita Mishra to kindly proceed with the presentation.
This is for Pratyaya sir, I got it.
Thank you. We are honored to have with us Professor Feridun Hamdullahpur, whose global expertise has enriched this course. We are fortunate to have his feedback on the course. Let us now listen to his reflections on this program, sharing his valuable insights. Miss Manisha Priyadarshini Tripathi. Mr. Sashir S. Kenganal. Miss Mitali Gowda. Miss Vidisha Majumdar. Mr. Pedina Sibakrishna. For grade cards, Mr. Manas Ranjan Behra. And Mr. Rohan Kumar Mahanta. Thank you, everyone. Next, we invite the feedback from the students on their experience and learning from their course. Participants, please feel free to share their thoughts.
Good afternoon all. I am deeply honored to share my feedback on this GIAN course. I am Manas Ranjan Behra, a research scholar at Mineral Processing Division of CSR MMT, and I'm working on a novel pulse-fed mineral scrubber that utilizes pulsative fluidization technology to clean ore materials and subsequently segregate fine and light particles. So this GIAN course has provided an insightful deep dive into various applications of fluidization technology, a technology that is pivotal for various industrial and environmental processes. Also, the lectures are very informative, or I can say extremely informative, and the hands-on experience offered a solid understanding how various fluidization types can be achieved in laboratory scale or pilot scale. Again, I'm planning to integrate the principles that I learned here in my experimental setup, optimizing techniques that can help to make my process more sustainable. Also in future in Indian Bureau of Mines that I'm going to join shortly. And finally, I would like to express my gratitude to the course organizers, speakers, team members, participants, for creating such an insight to such an stimulating learning environment. Thank you. Thank you.
Thank you, Mr. Manas. Anybody else? Yes, sir, please.
Good afternoon, everyone. Respected dignitaries on the rise, and my faculties and my friends. It was a nice course. For the last 5 days, I was attending this. It may gave us a certain idea about what are the fluidization bed about, what are the different applications. As you know, the hot topic nowadays is the waste management and sustainable environment. So this really topic helped us in giving us some idea about what are the different applications we can do by using fluidized bed, different type of fluidized bed that may be hydrothermal or three-phase, two-phase, and how they can be used in our environment upgradation. Because in industries also, you can know that now CO2 combustion, CO2 utilization is the main problem that everyone is trying to solve it in different industrial level also. So using fluidization, how you can use it for syngas production was also an interesting topic. And also with our faculties giving us some ideas and foreign faculties, we can have a breeze of knowledge that how then outside India, how they are proceeding the work, how they are carrying out the experiments, and what are the plans in foreign as well as in India also by our London faculties. They have also given us some idea about how the fluidization and how its applications is going on, and what are the advances that have been taken place, because fluidization process is one of the old process, in chemical engineering. So it gave us, I can tell in guarantee that it gave us a good knowledge, and I also thank madam and sir for giving us some visualized laboratory experience also, where we factually seen what actually the fluidization bed looks like, how it works, what are the different type of fluidization bed. Because looking at the PPT and visualizing is one different thing. Visualizing something will stick to your mind, for lifelong. So that also helped us a lot. I personally give my gratitude to all the coordinators, Mr. Madam Abanti and Jena sir, for conducting such type of GIAN courses that will help for us to know and increase our knowledge on a particular topic, and that is also a vast topic or sustainable environment. Thank you once again, everyone, to NIT Rourkela also for conducting such a topic on GIAN. Thank you.
Thank you all the participants for sharing your feedback, which will help us further enhance future programs. Gratitude is essential for every successful event. To extend a formal vote of thanks, I now invite Professor Mohan Jena, the course coordinator. Sir, please.
Esteemed dignitaries on the dais, Dean Srik in charge, Professor Santanu Behra, Professor Susmita Mishra, Head of the Department of Chemical Engineering, the course coordinator, Professor Abanti Sahoo, my faculty colleagues of the dais, dear participants, present offline and online, a very good evening to one and all. At the end of this 5 days GIAN course, and at the end of this concluding session of the course, I feel privileged and to offer the vote of thanks. My sincere thanks goes to Professor Santanu Behra, Dean Srik in charge, to present here, giving his valuable time and the valuable thought he has given and insight and the right information about the after the Fukushima disaster happened, nuclear disaster, how the scenario has changed, and many people again looked back for this energy from coal. So with time actually the technology is changing, but we talk about the renewable sources of energy, solar energy, hydrogen. As you know, hydrogen is not a primary source of energy, it is a vector in energy. So coal, combustion, syngas or electrolysis of water, we get hydrogen, but it is not a primary source of energy. But coal, the fossil fuel like coal we avoid because of the environmental pollution it causes in terms of the ash, because coal contains a lot of ash. So during its combustion the ash is generated, whether it is bottom ash, fly ash. Okay, so solid waste management is there, and apart from that carbon dioxide is another issue. So since long this the utilization of carbon dioxide, the carbon dioxide capture, sequestration, a lot of work are also going on, but tremendous potential this fossil fuel that coal is having, and the energy from the coal mostly we get by the technologies which use this fluidized bed. Fluidized bed coal combustion we know. With the advancement of the carbon dioxide capture, sequestration or other like fly ash management if we have, then coal will last longer. Huge resource of coal is available not only in India, in other countries also. So I am very thankful to Professor Santanu Behra. He rightly said about the countries they looked back to this coal technology. My sincere thanks goes to Professor Susmita Mishra, Head of the Department of Chemical Engineering, for providing all sort of support and encouraging us in conducting this GIAN course in the department. And definitely this GIAN course will add some page to our department activity. My thanks to Professor Abanti Sahoo, the coordinator. She has actually taken all the pain from the beginning, and also we had come with such a situation that we had thought of to postpone this course. Actually, she came back to this particular hall at the midnight at 12:30. Then we decided next day, okay, we are going to have this course. And the local coordinator also, he had at 10 p.m. he told that you just morning inform me whether I am coming for the inauguration or not. We had landed at such a situation. Anyway, so and my special thanks to my faculty colleagues. More than me, the contribution of Professor Akhilesh Sahoo is there for making the arrangement. Other faculties are not present, like Professor Mahendra Chindala, Adhidesh, Professor Adhidesh, and other faculty colleagues who are present here. Okay, your support has made this course possible. I am thankful to all the participants, offline and online, that without your this participation, this course could not have come to a success. And my special thanks to the Ministry of Education for providing this such a platform, that is GIAN, so that the foreign faculty are able to teach us or our students. And IIT Hyderabad also, the national coordinator, and I am thankful to Professor C.C. Sahoo, the local GIAN coordinator of NIT Rourkela. And at the last, I thank all the volunteers, because tirelessly they have helped us. Morning, evening, they have worked very hard to make this course a successful one. Thank you all. Thanks.
Thank you, sir, for expressing your gratitude and for acknowledging the efforts of everyone involved. This brings us to the end of the valedictory function. Thank you all for your participation and contribution to making this course a success. I now invite you all to join for the high tea and networking. Thank you. Before that, I would like to have a group photo. Sir, please.
Somehow someone recommended my name and says George and Rudolph he is vice president of TU Darmstadt. So he drafted me into that panel who will suggest what are those features that we should add that system ranking for the redefining thing. So तार बहुत दिन परे उटे global timing fix है जी about another 10-15 minutes from now. I need to go prepare something and sit for the
होटल